Welcome back to Chem 4300. In this video, we're going to continue Chapter 8 on classical wave motion. And now we're going to turn our attention to 2- and 3-dimensional waves. Now, in the first part of the chapter, we learned about 1-dimensional waves by solving D'Alembert's classical wave equation. And we introduced a number of important concepts like Fourier series analysis and Fourier transforms and waves in dispersive media. And all of those ideas will carry forward as we go to higher dimensional waves, 2 and 3 dimensions. And these will include waves like water waves, seismic waves, membrane waves like waves on a drum head, and even electromagnetic waves, light. So what we're going to do in this video is we're going to focus primarily on just 2-dimensional waves and the simplest possible two-dimensional waves. But as we get into the later material, you will see that the math is going to get pretty difficult, and some of the differential equations are going to be quite a challenge to solve. And in fact, I'm not even going to expect you to be able to solve these differential equations, but I want you to see how they're obtained and what the solutions are to those differential equations. So let's go ahead and dive in and take a look at the wave equation generalized to 2 and 3 dimensions. So this was done by Euler shortly after D'Alembert, and the form of the equation is this. It looks very similar to what we learned earlier. I'm going to change the symbol I'm using for the wave function from f to this Greek symbol psi. So psi is going to be a function of position, which is now a vector quantity in 2 and 3 dimensions, and also time here. And so we see on the left-hand side, there's the partial derivative with respect to time, the second partial derivative, and then we see it's equal to Vp times this thing which is called the Laplacian operator, which is this nabla symbol squared, operating on our wave function. So this Laplacian operator is just a recipe that tells us that whatever it operates on, do this. And in 2 dimensions, it says take the second partial derivative with respect to x, and then with respect to y, and add them together. In 3 dimensions, it just does that with x, y, and z and adds them together. So this is the wave equation in 2 and 3 dimensions here. And so now let's take a look at how we might solve this. And let's start with just 2D. And so written out, and a little rearranging here, I've written the wave function, partial with respect to x, the second partial with respect to x, the second partial with respect to y, equal to 1 over Vp squared times the second partial with respect to time. And now what we're going to do is we're going to take the same approach as we did in 1D cases. We're going to say that the wave function that satisfies this differential equation can be written as the product of a wave function with respect to only x, only y, and then only time. So this is called the separation as a variable approach, which we saw earlier. So if I plug this into my partial differential equation and apply it through by taking the partials, you'll see I'll get an equation that looks like this. So the part that only depends upon x operates on x, and y and t just sort of slide through. Similarly here, what operates on y, there's no dependence on x and t, so these guys slide through. We just have the partial with respect to y. And then on this side, finally, the x and y terms are unaffected, and then we just have the partial with respect to time. So if I divide both sides by the wave function, I can do a little rearranging, and I can put it in this form. And again, this might look familiar from what we had done earlier. And what I have now is a partial differential equation where everything that depends on position is on the left, and everything that depends on time is on the right. So what I'm going to do is set this equal to a separation constant. So we did this just like before. And this constant, which I'm in anticipation of what's going to come, I'm going to make it not just some constant, c. I'm just going to make it minus omega squared, because this will turn out to be useful later. And now this will allow us to turn this part of the expression here into an ordinary differential equation involving the time part. So let's do that. So now that goes from, go back to the previous slide, that was a partial derivative differential equation, and now we have ordinary differential equations. But that also leaves us with a partial differential equation involving x and y. And that's now equal to the separation constant that we just determined. So let's just continue to iterate on this approach. So I'm going to rearrange this expression, put all of the x-dependent part on the left, and what I have on the right is everything that depends only on y. Everything else over here is just constants. So once again, I can define a separation constant. In this case, I'm going to call it minus kx squared. And I can turn this partial differential equation involving x into an ordinary differential equation. And then once I'm done with that, I can do another redefinition and define ky squared is equal to omega squared over vp squared minus kx squared. And then I convert the partial differential equation that we started with into three uncoupled ordinary differential equations. So now we have the time ordinary differential equation, the x ordinary differential equation, and the y ordinary differential equation. And in that conversion, in that process, we found this constraint that omega squared over vp squared must be equal to ky squared plus kx squared. Okay? All right, now we have these differential equations. We've solved these before in the beginning of this chapter, so we know the solutions to these can be just simply sinusoidal solutions, which we'll write in complex notation. So this has a simple sinusoidal solution, this has a 1, and this has 1. So we will write them all together as this product here, and that's our simple sinusoidal solution that satisfies these three ordinary differential equations and, of course, our partial differential equation. Okay. Now, if I take that solution there and I do a little rearranging, I'm going to group together the part that depends on space here. So kx times x plus ky times y into this term here. And this part right here in the exponent, this term, I can actually identify as a product of a vector that I'm going to define called the wave vector, k, which is the dot product of that k with the position vector. So in other words, I'm going to define a new quantity called the wave vector, which is equal to kx times the unit vector along x plus ky times the unit vector along y. And if I take the dot product of that with the position vector, then I obtain this quantity up here. So I can then simplify this in a way by introducing a new quantity and write this expression as a times e to the I k dot r, where these are now vector quantities, minus omega t. So this is an important new introduction here, because we've learned before that k is not just 2 pi over lambda in the one-dimensional case, but actually k had a sign which told us where we were going left or right. But now in 2 and 3 dimensions, we see that k becomes a vector. So it tells us more than just left or right, but now it tells us which direction the wave is moving. So k defines the direction of the wave propagation. And the size of k is still going to be 2 pi over lambda, and you can also write it this way too. But this vector quantity now is going to tell us the direction in which the wave is moving. So if we think about it this way, then kx times x plus ky plus y gives us a phase that's in our argument for our sinusoids. And that phase is going to be constant in our wave along a line. So in other words, there's going to be, if we think about our two-dimensional wave, there'll be lines of constant phase, and the k will be a vector that's perpendicular to that line of constant phase, and that's going to tell us the direction in which the wave is propagating. So you might want to call this a line wave in this two-dimensional case, but in 3D it becomes a plane that's moving, and so we're just generally going to call this k is defining the direction in which the plane wave is moving in this example here. Okay. So this is an important concept then, that k now goes from 1D of telling us whether the wave is going left or right and what the wavelength that's associated with it, to now telling us that we have a sinusoidal wave in multiple dimensions here that now has a direction and also a wavelength. And they're all contained inside this vector quantity. Okay, so next what we're going to do is we're going to look at a wave that's bound by constraints. So this is a little picture I found here of a square drum here. So let's look at something like this, where we have a wave that can exist on this membrane, and we have constraints that it has to go to 0 amplitude along the edges. So you can imagine just some rubber sheet stretched over the opening of a rectangular box, and you glued it around the side. and we know that the standing wave has these supports at x equals 0, y equals 0, and then x equals Lx and y equals Ly. Those are our boundary conditions. We know that the wave function has to go to 0 along the edges. So for these two edges, we know the wave function has to be 0. And similarly, we're going to know on the other edges as well. So first of all, just by doing this, we know that our solution can be simplified to this form. And then when we put in the other boundary condition, then we find that in order to make this true, to go to 0 at these 2 points, we have to set kx Lx equal to n times pi, where n is some integer. And so that this argument here is some integer multiple of pi in order to satisfy this condition of the wave function going to 0. And then similarly for ky times Ly, that has to be some integer multiple of pi in order to make this argument go to 0 when the wave hits that edge there. So these two boundary conditions allow us to rewrite our solution so that we have these constraints. And so now we know that from what we learned before from the frequency, that the frequency is equal to Vp times k. So now we're going to write it in this form. So the frequency is now going to be indexed by n and m. So remember in the 1D case it was just indexed by n, but now it's going to be indexed by n and m. And these k values, which are constrained, now we'll have these values. So if we rearrange these to solve for k, we see that omega is going to be Vp times the square root of, now we have n pi over Lx squared plus m pi over Ly squared. Those are our values for omega. Now if we went to a square box where Lx and Ly are equal to each other, so just L, then we can simplify this one more step and just pull the L out, and we have it's just pi Vp over L, the square root of n squared plus m squared. So this is analogous to what we saw in 1D case, but now with 2D we have two integers, quantities, n and m, which are needed to satisfy the condition that our boundary conditions, the wave function, go to 0 at these points here. Okay, and one of the things that you notice in this square box case is that there will be different values of n and m that will have actually the same frequency. So if n is equal to 1 and m is equal to 2, then that will have the same frequency as if n is equal to 2 and m is equal to 1. So these are what we call degenerate frequencies. So different indices of n and m actually end up with the same frequency. And this is something we'll come back to later in this chapter and then later when we get to quantum mechanics. So then what we learned in that case was that this generalization of the 1D when we're looking at the string and with the boundary conditions, now we have a drum with boundary conditions. We're going to have this two-dimensional wave where there's some amplitude for this normal mode, and then we have the spatial oscillation and then the time-dependent oscillation. So any wave on this rectangular membrane can be written as a superposition of these normal mode vibrations. So here we have our normal mode, and we can add them up with different amplitudes, and we can get any solution for the wave function on the drumhead here. And of course, we know how to do Fourier series analysis. We do this in 2D. So again, just an analogy with what we did in the 1D case, we can take any wave function here, do a Fourier series analysis, and we get this result here for decomposing back into the original amplitudes of each normal mode vibration that's in the drum. And that's the approach. So if you, for example, looked at some of these normal modes on a rectangular drumhead, they might look something like this. So here's, if you had just say m equals 1 and n equals 1, these are this white and green are representing the different phases. So when the drum head is, say, above the equilibrium position, and green when the drum head is below the equilibrium position. So here you see this is sort of a snapshot at an instant in time where all of the drum head is above the equilibrium position, and this would be occurring when you have m equals 1 and n equals 1. In this case, when m equals 2 and n equals 1, then in this normal mode, half of the drum will be down and the other half of the drum will be up. And m equals 3 and n equals 1, then we have one part down, middle part up, or I should have said up, and then down, and then up. And then if you go flip it around the other way, where n is equal to 2 and m equals 1, then you'll have this part up and this part down, and so on. So this is what the pattern will look like in this two-dimensional drum. Okay. So what I'll do in the next video is I'll run through this web app here, and we'll see in sort of a real simulation of a rectangular membrane wave how these guys, normal modes, can be oscillated, and how we can decompose any drum pattern. So if we hit the drum with our hand or with a stick and we create some kind of wave on the drum, how we can decompose that into the sinusoids. In the same way that when we plucked the string, we saw that we can decompose that into all the sinusoids. We can do this now in 2D with a 2D Fourier series analysis.